Hey there, this is Arnav from Pebble, and welcome back to the Introduction to Linear Algebra series. In this video, we wanted to go over subspaces, and in the last one, we went over vector spaces. So these two topics are very much interrelated. And so, what is a subspace? Well, to answer that, first we need to think about, let's say we have a set S. Okay, the set S has some objects that are vectors, and we're just going to say it's not equal to it's not empty. Okay, so the set is not empty, and for S to be a valid for S to be a valid vector space, we need to confirm those 10 propositions that we covered in the previous video. They need to all be true, those addition ones, and then also those scalar multiplication ones. But this is a hassle in a lot of cases. So what if this set S, what if all the objects of S are belonging to another set V? But this time we know that V is a vector space. Okay, so V is a valid vector space. V has been verified by all the propositions before. And so this vector space, V could be anything, right? It could be any vector space that just contains the objects in S. And so what that does is, well, these objects belong to V, and V is a vector space. So by that, it should follow that there should be less rules because some of them are already guaranteed to be confirmed. So what propositions do we have to confirm for S to make sure that it is also a vector space? Okay? And so we basically only need two properties, which are the two closure properties that you see. So we need to make sure that S is closed under addition, which means that if two vectors u and v belong to S, then u plus v is also going to belong to S, pretty much. And then remember the scalar multiplication one is that if u belongs to S, then, and we also have alpha is any scalar, then we know that alpha dot u has to belong to S. So if this proposition and this proposition both turn out to be true, then, and we know that S belongs to V and V is a valid vector space, then S has to be also a valid vector space. And what this is that we call it a subspace. Okay, so it's a subspace of V if and only if these two conditions hold. And we call it a subspace because it is a vector space that belongs, all the objects belong to another vector space. And so if you were to go through and try and prove all the other propositions, so if we took a sample vector space V and then we took a couple if you took an example S that belonged to that vector space and you tried to prove all the propositions, then you would indeed end up with all 10 being proved, but you really only need to focus on these two closure ones while you're actually checking in an actual problem. So that's why subspaces are just so useful. Okay? And they're just amazing because of all of that. So I have an example here that I want to go over. So let's say that we have this vector space A, B, C, D, which belongs to all the 2x2 matrices, but B and C are both going to equal 0. So take a moment to think about how we can use this idea here of just having two propositions that we need to prove. What could be what's our S in this situation and what's our V in this situation? So take a moment to do that, and after you come back, we'll go through the problem together. Okay, great. So hopefully you identified that whatever this is, this set is your S, and then what V would be is just M all 2x2 matrices, because this is a vector space. It's all 2x2 matrices. We don't need to go into we don't need to prove that this is a vector space, because it just kind of logically follows that if you have a set of every single possible 2x2 matrix, then that has to be a vector space because it's closed for literally everything. You can't exit the vector space. Everything works. All the propositions just logically should work. And so we don't really need to go into that much of proof. Okay? And so now all we need to do is verify closure in S under matrix addition and scalar multiplication, right? So let's take some arbitrary elements just because we can't know exactly what the elements are, because it's really just unbounded. And so let's say we have a U that belongs to 2x2, and U is going to be A. Remember, B and C have to be 0, and then B down here. So these two have to be 0 as per our definition of S. And then we also have V, which is going to be, let's say, another vector, another matrix, C, D in the top left and bottom right. And so if we were to add these two as per our just simple matrix addition, and I have to use the normal plus here because they're not vectors. So we'll get A plus C, 0, 0, B plus D. And so this matrix are elements in S, because these two are just real numbers. They're gonna, if you had actual numbers, they're just gonna solidify to actual numbers. And remember, these A and D can be anything as per our definition. Only B and C are constrained to be 0, and B and C are staying 0. So because these two spots can be anything, then this would still belong to S. So that validates the addition closure property. And then we need to do scalar. So if we have scalar times our U, right? So scalar alpha, then we're going to get alpha A, 0 in both of these, because scalar times 0 is going to be equal to 0. And then alpha B. And so once again, these two spots can be anything. So this would also belong to S. Okay? And since both of them are elements in S, then it follows from our two propositions for a subspace that S is indeed a subspace of M 2x2. So S is subspace of M 2x2. And so, since we know that, subspace is just a vector space. So that means that S is indeed a vector space. S is a vector space. Okay? And so I hopefully that example made sense as to why we were able to use these two propositions. And we're going to call this the theorem. Okay? I'm not quite sure of the name, but we're just going to call this our vector space theorem, or subspace theorem rather. And so hopefully we were able to use that subspace theorem to show that this would be our V, and then this whole thing would be our S, and we could show how, well, this is a subset because we have the belongs to, and this is a valid vector space. So that's going to mean that we just got to confirm these two propositions like we did. Okay, so let's do one more example. And this example is going to be, let's see, I don't know which example I want to do. All right, let's do this one then. So we're going to have S, our subset S. It's going to be X, Y, Z, so we got a three-dimensional vector, or well, we're going to say this is a row matrix. And that belongs to the set of three tuples, but y has to equal 0. So I think we did this example once before for in the previous video, but this is now for subspaces. Okay, and we need to determine whether this is a valid vector space. Okay, and so R3, from the same logic as M2 by 2, this is vector space. So this is a vector space. So we only need to consider our first theorem, our subspace theorem, which is those two propositions. And so considering those two propositions, let's say we have two arbitrary elements. Say we have U, which is going to be A0 and then B. A0 and then B. And then we're also going to have V, which is going to be C0D. And then add them together, you're going to get A plus C, 0, and then B plus D. And since we know that A plus C and B plus D can be anything, and X and Z can be anything, well, Y has to stay 0, this is indeed validated by a closure. And then if we were to do scalar, so a scalar times U, then we would just get alpha A, 0, alpha B, and you can see that this is not getting violated in any way, shape, or form. Okay, so that means that S is indeed a vector space. And so now I'm going to give you another example where we don't have the 0 now. So this is going to be S equals, again, the three tuple, so X, Y, Z, it's going to be three tuple, and it's going to belong to the set of all three tuples, but this time X is going to equal 3. So go ahead and try this one, and tell me if it is closed under addition and also scalar multiplication, and once you come back, we'll go over it together. Okay, great. So hopefully you had a chance to do that, and you should get the answer that this isn't a vector space. And the reason why is, let's take arbitrary elements. So let's say U is going to be 3YZ, and then V is going to equal 3AB. And so once we do this, we want to add these two because they have to be closed under addition. So we're going to get 6 Y plus A and then Z plus B. And something you can see here is that whatever in our X space, this is no longer a 3, which means it will not belong to X. It will not belong to S. So because it's not closed under addition, we don't even have to check scalar multiplication, even though that wouldn't be either. And so because it's not, then this means that this indeed is not a vector space. So it's not a valid subspace, which means it's not a vector space. It's not a vector space. And so that example is one of the examples where it will not, this theorem, it might look like it applies, but it's going to actually just tell you that it's not a vector space. And so this comes to another theorem that we need to talk about, which is basically just if you have a vector space V, then and you take a subspace of it that's just the zero vector, this is gonna be a subspace. Okay, and this is pretty easy to follow just because, well, if you take two of these, you're just gonna get the zero vector, and then any scalar times the zero vector is just gonna equal 0. So this is gonna still belong to V because it's not changing. And so yeah, that is a valid vector space. Okay, and then one more theorem is that if you have this a non-empty subset S of a vector space V, then it is a vector space of V if and only if whenever U and V are two elements in S and alpha and beta are any two scalars, then their linear sum is also going to be in S. So basically, if you have two scalars, alpha, and then a vector U, an element U, and then beta times element V, if this belongs to S, then that means that it will indeed be a valid subspace. Okay, and this is if and only if. So if this is not true, then it's not going to be as well. Okay, and this is kind of just an extension to this previous one. This is just kind of like a linear combination of the two, which is just important. It's important to note and make abundantly clear when you're learning this. Okay? And one more thing to go over is we want to understand, well, what about these linear combinations, right? This is a linear combination here. So what is there something we can call linear combination? And yes, there is. So let's take this polynomial set t squared t and 1. So t is just a variable, and this just belongs to the set of all polynomials that polynomials 2. So this is just all quadratics, and so this would be, your variable. And so all quadratics, the span of S, we're gonna call this term span. This just means the set of all linear combinations of a finite set of vectors. So if you have this is a finite set because it's limited, then the span of S is just going to be the set of all linear combinations that you can make with these three and any scalars. So the span, so we're going to say, so we're going to just call this, we're going to say this is S. So the span, and we denote span like this. So span parentheses S. And so the span of S, this can equal the set of all linear combinations that we can make with this. And so that's just going to be all polynomials. So that's just going to be P2. So this is just, it's a bad example, but basically just to show you that span means all combinations, and you can make any quadratic with this. So it's just going to be all quadratics. Okay? And one thing to note here is another theorem. The span of a set of vectors S. So if you have where S all belong to V and V is a vector space, then the span of S is gonna be a subspace of V. And I want you to try and prove this on your own. I'm not going to do it in the video, but it is a good proof to try and figure out yourself, although it does get a little bit complicated. But just remember to take some sample elements and, try to represent the span in a way that you can. And so one last thought to leave you off on. If you have a set of vectors in a vector space, and W is a subspace. So S is your set of vectors, and then you also have another subset, W, which is a subspace of V that has all of S. Then W will contain all the vectors in span of S, which is kind of weird to think about, but S belongs to V, and W belongs to V. W is sub. And then S belongs to W as well. That means that span S will belong to W. Okay, because W is a space, which means that it's gonna be, for our purposes, for what we've learned right now, it's gonna be infinite. Okay, it's an infinite stretching in both ways based on the conditions. So the span of all the linear combinations of S are gonna have to belong to W because all of S is in W, and W is from this idea here. Since all of this has to belong to W for it to be a vector space, then obviously all combinations are gonna be in W. And so yeah, that concludes subspaces, which is a pretty big topic to understand, subspaces and span. So this video was a bit longer, but hopefully you understood the general idea, and I'll see you in the next video.